Okay, today we will begin our journey into understanding digital electronics. The first thing we're going to cover is binary. Well, what is binary? Binary, it's a base 2 number system. What exactly does that mean? Well, to put it in perspective, we use a base 10 number system. Well, that means that we start at 0, we go all the way up to 9, and then we add a new digit, and we start again. So you see, we start back at 0, and then we keep track with this 1. And it's called base 10 because we have 10 numbers to work with. We go through 10 numbers before we start a new digit. Base 2 means we start at 0, we go to 1, and then instead of writing 2, we start the count again. So we drop back to 0, and we keep track with the 1 in front. And here, there are only 2 numbers. So how do we know this clearly looks like a 10? If you just wrote this on a page, I wouldn't know anything else. So we always denote it as this 2, and we denote base 10 with a 10. That way we don't get confused while we're working. Now, what a lot of people get confused with is they treat binary like its own thing, really. Binary works the exact same as base 10. It's just we end our counting a lot sooner and we add a new number. That's all it is. We're just starting it off sooner. Now, let's look at some binary numbers. 0, that becomes 0. So, this is in decimal, this is in binary. Well, 1, that becomes 1, and 2, that becomes 10. So you can see 2 is where we get our first overflow sort of thing, where we add 1 and then we drop our count back to 0 and we start counting again. 3, well, that's 1 1. 4, that's 1 0 0. You can see we got this, and then that filled up to become 2. So that became a 0 when we added it. This became, we carried the 1 over, and then this became 1 plus 1, and that gave us 0. And so we get this. And then we look at 5. That's 1 0 1. What? 5 is 1 0 1. 6 is 1 1 0. You can see that overflow. 7 is 1 1 1. And 8 is 1 0 0 0. And you can see the whole new number was added. And if you look in the pattern of where these were added, you get 2, you get 4, which is 2 to the power of 2, and you get 8, which is 2 to the power of 3. And this keeps going. At 16, we'll get a new digit. At 32, all these powers of 2. And when you actually look at base 10, you'll see the same thing. We get a new digit at 10. We get a new digit at 100, which is just 10 to the power of 2. We get a new digit at 1,000, which is just 10 to the power of 3. But let's say we're just given a random number in binary. How the hell do we know what it is? Let's just pick a number at random. 0, 0, 1, 0, 0, 1. Well, let's take a look at our pattern again. So this, the value in the very first digit, that's going to be 2 to the power of 0. The second digit, well, that's where we get 2 to the power of 1. That third digit is represented by 2 to the power of 2. The fourth, 2 to the power of 3. So how many digits do we have here? We have 1, 2, 3, 4, 5, 6. So this will be 2 to the power of 5. Because remember, we started at 2 to the 0. Now, how we're going to calculate this now is we're going to add the numbers. So we're going to say 1 times 2 to the 5. And then we're going to say 1 plus, and then we're going to say plus 1 times 2 to the 4. Plus 1 times 2 to the 3. We are basically adding these digits together. So this can be represented as 32. And then this is represented, no, sorry, this is represented as 64. This is represented, no wait, this is represented as 32. This is represented as 16. This is represented as 8. And then because this is going to be 0 times 2 to the 2, this is going to be plus 0 times 2 to the 1, because there's no values there, and then we're going to get 1 times 2 to the 1. And this will give us 32 plus 16 plus 8, and then plus 1. 32 plus 8 is 40. 40 plus 16 is 56. And we get 57. But how do we know this works? Well, let's take the number 6, for example. That 1 there, well, that comes from 4, which is 2 to the 2. That 1 there, that comes from 2. And then, well, this value here, that comes from 0. That's 0. 4 plus 2 plus 0 gives us 6. So now we've just figured out that if we want to, we've just figured out now that if we want to convert binary back to decimal, we need to times 2 to the power of n, where n is just 1 less than the number of digits, than the number of digits that thing represents. I explained that really badly, sorry. Where n is this number, so 1, 2, 3, 4, 5 minus 1. Now, let's say we have a number in decimal. Let's take the number 57 again in decimal. And now we want to convert it to binary. Well, we're going to just divide it by 2 at first. We're going to take this number and divide it by 2. Why? You'll see in a bit. So 57 divided by 2 gives us 28. But then we get a remainder of 1. and then we go 2. That gives us 14, which gives us a remainder of 0. 2 again gives us 7 with a remainder of 0. Divide by 2 again gives us 3 with a remainder of 1. 2 gives us a remainder of 1, gives us 1 with a remainder of 1. And then divide by 2 one more time. Well, that just leaves us with 0 and 1. Now, why did I make a point to put all of these numbers here? If you look at it, this number, it looks vaguely similar to this one. But can we prove that it's the same number? Well, let's look. This is 2 to the 1. And when I divide it by 2 again, I get 2 to the 2. And then 2 to the 3. And then 2 to the 4. What about this? This gives me 2 to the 5. And this gives me 2 to the 6. Well, this 1 is the now, well, this 1 right here, that is the remainder of 2 to the 1. That means this 1 is less than 2 to the 1. And that means 2 to the 1 is 2. So the only number that could represent is 2 to the 0. Now, let's take a look at the next one. That is the remainder of 2 to the 2. So it must be, this 0 must be less than 2 to the 2. But it also can't be 2 to the 0 because that's this number. So what this essentially means is that this 0 will represent 2 to the power of 1. Now, this is weird how it works because we took out our remainder first. So then this is a new number. I might need to cut that. Oh well. So, now this represents 2 to the power of 2, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and 2 to the power of 5. And when we go back and look at our numbers for 57, we can already see it. That 2's there, that 2's there. And basically, how we do this is we call this piece right, this number right here, that is our MSB. That is our most significant bit. It's the highest bit in our binary number. Bit basically means the number position. So if I say this is a 6-bit number, Well, that means there are just 6 digits. And this is our LSB, our least significant bit. This is the lowest bit, or the lowest number in it, the lowest digit in it. So I've now basically proven that this number is 57. I've proved it going from binary to decimal, and I've proved it going from decimal back to binary. But now, what happens if we get a number that isn't whole? What happens if we get 0.33, let's say? Well, let's take a look at this number. If we follow the same method as dividing by 2, well, that number is already less than our starting point of 2 to the 1. I mean 2 to the 0. That's already less than 2 to the 0. It's less than 1. So we can't divide by 2. That won't work. If we want to get this number towards 2 to the 0, we're going to need to multiply it by 2. So we're going to say 0.33 times 2. Because 0.33 is in 0.33. Sorry, gonna need to edit this out. What this number is, it's 2 to the negative something. I'm going to call it n. This is in the negatives, and if we want to get the negatives to positive now, we're going to need a times by 2. We're going to follow this pattern. This 2 times this 2 times this 2 times this 2 times this 2. But instead of dividing the number, we're going to follow this pattern and times it. So, if that's a bit confusing, let me demonstrate. This is 0.33, and we're going to say 0.33 times 2. That gives us 0.6. Now, what we're going to do is see, is this number greater than 1? No, it's not. So that's 0. Because if it's greater than 1, it means it's greater than 2 to the power of 0. Which means it's greater than our first bit. So, 0.33 times 2, 0.66 times 2. Well, that's going to give us 1.32. And you notice that this number is greater than 1. It is greater than 2 to the power of 0. So what we're going to do is we're going to take that and we're going to minus 1 from it. And then we're going to say 0.32. And that 1 becomes our remainder. Times 2 is 0.64. That's going to give us a remainder of 0. And now 0.64 times 2 is going to give us 1.32. Now, this can go on and on and on until we reach 1. Until this number here equals 1, you can keep going. So, what it's best to do is stop at a certain number of digits. I'm going to stop here at 4 digits. And now, the part that sometimes might confuse people is the most significant bit is the top one now. That is our MSB. Why? Because now we are multiplying instead of dividing. So this is our smallest number. So this, okay, I might need to cut this. So now we are multiplying instead of dividing. So our MSB will now swap places, and this becomes our LSB. Okay. And that's basically the basics of conversion done. Now, let's look addition and subtraction for binary numbers. Well, when we add two binary numbers, let's say 4, which is 0, 0, 0, and 5. We're going to add these two. So this is 4, this is 5. It should become 9. Well, this becomes 1, 0, and now we have two 1s, so that will become 0, and we're going to carry the 1. That becomes 1000. So this is equal to 9. Binary addition is very, very simple. Now, let's say we have a number like, let's do 101 minus 100. So let's say 4 minus 5. 5 minus 4 now. It's going to be 5 minus 4. Well, this will be 0, 0. This will be 1. That'll give us 0. That'll give us 0. And this gives us 1. So it's also pretty simple. But now there's a technique we need to learn, because binary is the language that computers use. And we'll get further into why computers use them in the next lesson. But for now, all you need to know is computers are not the best at adding and subtracting. I mean, no, they're good at adding. They're not the best at subtracting. So we need to find a way to turn this into addition. And the method they found was called ones and twos complement. Ones complement basically takes this number, the number we are minusing by, so 100, 100, which is 4, and it changes it by flipping each bit. And what that means is basically we're going to swap the bits around. We're going to make 1 0 and each 0 1. So the 1s become 0s and the 0s becomes 1s. And now 2's complement changes that number into, now 2's complement takes that same number and adds 1. So actually in this case it's kind of funny, because it gives us 4 anyway. I mean, yeah, sorry. Here we go. This number will give us 4 anyway. So it is kind of funny. But now, when we take 1's complement, we're going to say 101 plus 101, 100. Now, we've seen the calculation. This gives us this. You might say, oh, that's 9. We did 1's complement. We did 1 and 2's complement. So this digit here is just ignored. It's thrown away almost. And the answer we're left with is 0, 0, 1, which is the same answer that we got here. And this method really helps with computing and these sort of things, which once again we'll get to in the next lesson. The thing is, we've taken a nice look at binary now. You've got the basic understandings of it, and you understand it's just another sort of number system. Well, binary is the main thing computers use, but it's not the only type of number system we have. We have 2 more. One is called octal, and the other hexadecimal. Hexadecimal. Sorry, I write very slowly. Octal is a base 8. That means it goes from 0 to 7, and then we jump to, and then we start the count again. Now, hexadecimal is base 16. But what you're saying is we only have 10 numbers. So we go 0 all the way up to 9. And then at 9, we go to A, and A goes to F. So, in hexadecimal, 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, 15 is F. And then at 16, we just begin again. And then at 16, we'll just go back to 1, 0. Now, converting octal and hexadecimal to decimal is the exact same as it is for binary. The only thing that we don't have to worry about is 1's and 2's complement for octal and hexadecimal. But when you're converting octal and hexadecimal to binary, there is a nice little trick we can use. So octal is base 8, which means that we naturally move up in powers of 2 to the 3. So now, if we want to find a quicker way to calculate, to convert octal to binary, let's take the number 17 in octal. When we look at this, this is 8 to the 0 times 7. And this over here is 8 to the 1 times 1, and that basically gives us 15. And we can convert that to binary. Though we can also say and break it up. So this, what is 7 in octal going to be? That's going to be 8 to the 0 times 7, which is basically going to give us 7. So 7 in octal, 7 in binary is just 1, 1, 1. And this 1, what is 1 in octal? That's going to be 0, 0, 1. And if we add these two numbers together, we will get 1, 1, 1, 1. Now we can check that number. Let's take this 15 and we're going to divide it by 2. So we're going to say 15 divided by 2 gives us 7, the remainder of 1. 2 gives us, you can already see the 15, we already have the 7. That 7 is the same there. And we just added the 1 from the first digit already. So you can already see it's going to work out. That 2 divided by 7 is going to give us 3, going to give us 1. That 2 is going to give us 3, which is going to give us 1. The remainder of 1, and that 2 is going to give us 0. And basically, we use the fact that 8 is just 2 to the 3. So basically, we are just using these numbers, that this number will be a power of 2 to the 3. So what this is essentially saying is 8, this number here is 8 to the 1, which is our 2 to the 3, 4. So this, okay, this number here, let's say, this number here is 7. And that is going to be, that's going to fill the 2 to the power of 0, the 2 to the power of 1, and the 2 to the power of 2. Because 8 is 3, is 2 to the power of 3. So 8 takes up 3 digits. Well, 8 takes up 4 digits of binary. But because we can only go up to 7, it takes 3. And now, if we do the same for hexadecimal, and I say, if I were to say 17 in hexadecimal now, that would be 16, that's 16, that would be 16 to the 0 times 7, which is equal to 7, and this would be 16 to the 1 times 1 to 16, which means this would be 23. Now, we're going to use the cheat code again, but now instead of using 3 digits, we're going to use 4. And this is going to become 0, 1, 1, 1. Notice the zeros are very important. It's very important to keep that 0 there. Because if I don't, I'll end up 1 digit short in my number and it'll all be wrong. So this is going to be 0, 0, 0, 1. Now, this is a 5-digit number. We can go and calculate this, but that's up for you to leave at home. Oh, there is the last thing we need to know is a BCD, or the binary encoded, no, the binary coded decimal, BCD. Now, a lot of people also get confused with this, but only use this if they tell you to use it. BCD basically takes the number, let's say 14, and this is in decimal, and basically encodes each number to a binary value. So BCD works almost the exact same way as hexadecimal. We're going to use 4 digits. So this is going to be 0, 1, 0, 0, and this is going to be 0, 0, 0, 1. Only thing with this though, the only issue with this is this number does not equal 14 in binary. This is not 14 in binary. It is not. This number is basically coded. I can't remember exactly where we use these in computers and stuff, but what I do know is don't get confused between this and hexadecimal. This number in hexadecimal, this trick by converting 17 to this and this in hexadecimal works. This number is 17 in hexadecimal. This number is not 14 in decimal. It is not the same. It is just, this is our 1 digit and this is our 2 digit. And often when you write things like this, you don't want to omit these zeros. You won't disregard them. You will still write the full number as 0, 0, 1, 0, 1, 0, 0. You will keep these. And that's about it. That is basically the entirety of binary. Thank you for your time.